Okay, now we're going to look at a different data set, so we could do some logistic regression. The data set is, well, let me just read it in and show you. Comes from the Titanic ship disaster. Each row of the data set is a passenger on the ship, and it has various information about the passenger, notably whether or not they survived the shipwreck, and has things like their name, sex, age, class, which is the class of ticket that they bought, ticket number. I guess this actually could be important. I'm not going to look at it here because I just didn't look at it, but this is kind of important because it tells us whether these people are from the same group. So like these 4 people, looks like 2 babies and 2 adults, and they all came from the same ticket. So that tells us, I mean, you can kind of get that by the last name, but that's not perfect, and you could get it from the ticket, but we're not going to look at that. Where they got on the ship, occupation, price they paid. This is a bit of a weird format. It has like the English pound symbol. So we won't look at that, but if you wanted to look at that, you might have to do some string manipulation to convert this to a number, because this column is a character vector. Job, which is usually empty. Survived. There's actually, I believe there's a web page with information about each person. The date they died. So this is, kind of important. So we're going to be modeling whether or not they survived. And you really want to make sure whenever you fit this kind of model to not include information that basically gives away the response as the predictors in the model. And so if you take a look here, these 3 people all died, so their survived value is 0, and the date of death is here as 4/15/1912, which is the date that the ship crashed. So you want to be careful using a variable like this in the model, because basically this gives away the response. Date of birth. So this is kind of similar to the age variable. And then there's some other things here. I'm not sure exactly what these are. There's a code for the age. I'm not sure what these are. Okay. All right, so let's take a look at some of the variables. Basic one to look at is the number of people that died and the number that survived. So basically most of the people died. But there were a significant number of survivors, 500 survivors. We can use the table function. I use the table function all the time for stuff like this. We can break down whether or not they survived by sex. So the first row is females. So 127 females died, 339 survived, 682 males died, and 161 survived. So this is going to be an important variable in our model, because if the passenger was female, she was more likely to survive than die, and if they were male, they were much more likely to die. All right, so that's an important variable. Class, this is the class of the ticket. There's 3 values. First class, 1, 2, 3. I believe first means first class, like the highest level of ticket, and 3 is the lowest class. So if you're in first class, you were more likely to survive, and less likely if you're in one of the lower classes. And I believe proportion-wise, this is the worst. Okay, so that's good to know. That's another important variable. We can look at a histogram of the ages. Let me clean this up. You could see that the peak of the distribution is in the mid-20s perhaps, or early 20s, and tails off. There were children on the ship. You could break down the the survived by age. I don't know why I have 2 lines here. Let me get rid of that. And so this is for each age, whether or not they survive. So for the youngest ages, it actually breaks it down into, I suppose this is, well, it's fractional years. And so there are a few babies on the ship. Many of them survived. So actually only 2 passengers under the age of 1 that died and several that survived. And then it breaks it down by each age. This is a bit hard to look at. So what we're going to do next is take this data and make a plot out of it. So let's do this. Save is that thing. So this says 2 columns, 0 and 1. And I'm going to try to add a new column called proportion, which is the second column, which is number survived, divided by the total number, which is the sum of the 2 columns. If I do that, I get a warning, converting left-hand side to a list. So don't ignore warnings, because now if I look at this thing, this is not quite what I wanted. I don't know why it's doing this. Well, I do kind of know why. If I do, so if I define this again, class save, here in this code, I'm treating it like a data frame or a matrix. Actually treating it like a data frame. And it's actually not. The class is not data frame, it's table, which is something different. And so apparently you cannot add a new column to a table by doing with $ operator. Let me try it a different way. I'm not sure if this is going to work or not. Apparently you can access it. You can access columns with their column numbers. Can you assign? No, that doesn't work either. You can't add a column. Can you cbind? So what I'm doing is I'm taking the original thing. That actually works. And it looks like the numbers are what they're supposed to be. So let's just take an example. Here, 4 died, 2 survived, so 1/3 survived. That makes sense. So apparently you can do it that way. You could convert it. You could try converting this thing to a data frame, but that actually doesn't work. You can run this code and look through it yourself, but this actually doesn't work either. So let's go ahead and comment that out. Another way of calculating the proportion for each age group is to use dplyr, group by and summarize in dplyr. So let me show you how that works. So I'm going to create, just a temporary object. I'm calling it SV, and then we're gonna use group by and summarize. So I'm piping Titanic to the first argument of group by, so grouping Titanic by age. And then we're going to summarize for each age group. The died is going to be the number that survived. Oh, sorry, number, that doesn't make sense. Number for which survived equals 0. So I'm just doing sum survived equals 0. The number that lived, whereas sum survived equals 1. And then the proportion is lived over died plus lived. And the way you conceptualize thinking about this, it's as if, so when we're looking at this code, we think about this as if there's an object called survive, which is one of the columns of Titanic, that exists in your workspace. But when you're accessing it inside summarize, you're accessing it separately for each age. So it's like you're looping over the unique ages. Each time you have a vector called survive, which is the survived values for that age group, and then you could do operations on it. All right, so let's take a look at this. Okay, and this also looks like it's doing the right thing. So for this age group, 0 died, 1 lived. Proportion is 1. For this age group, 1 and 1, so it's a half. Okay, that makes sense. And then we can make a plot. Okay, so that's the plot of the proportion for each individual age group. It looks like there's generally a downward trend. Basically, everyone over 65 or so died. And then don't get too fooled because it is going up, I think, but it's easy for your eyes to discount these things. Really what we should probably do to make a better plot is make the circle size proportional to the number in each group, the total number of passengers in each age group. So as an exercise, you can try calculate another column that has the total number in each age group and use CEX to change it. Okay, so we won't do that here, though. Okay. All right, so those are the main variables. We're going to look at sex, class of the ticket, and age. And the way you do a logistic regression in R, simplest way, is instead of the LM function, you use the GLM. GLM stands for Generalized Linear Models. The syntax for specifying what variables are in the model is exactly the same. Here, I'm not putting spaces between the pluses just because I want it all to fit on one line. But this is exactly the same. Say the data set. And then in a generalized linear model, you're not specifically assuming that the residuals are normal. So you have to tell it, unless you want to assume normal, because that's the default. But if you don't want to assume normal, you have to tell it what distribution you want the responses to have. So we're going to model the response, survive, which is 0 or 1, as binomial. And by default, if you specify it this way, it assumes that there's a failure character, in this case 0, and a success character, in this case it's 1. And that's exactly how survived is coded. If you wanted to do binomial with each row has like multiple successes and failures, you specify the model a different way. Basically, you have to give it a 2-column object here. So if your data is not 0 and 1, success failure for each individual person, basically it's grouped by different groups with number of successes, number of failures. You specify it a different way, and you really should look at the documentation for GLM because it's a bit surprising how it gets done, but once you read it, it does make sense. So look that up. Okay, so there's fitting the model, fits very easily. If I do summary, this is the output. And okay, so what do we see here? Basically what a logistic regression does is it models the response with a probability of success. In this case, success is survived equals 1. And if you look at these numbers, the intercept is 4.5, which is obviously not a probability because probabilities need to be between 0 and 1. By default, it transforms the probabilities using what's called the logistic link function, which we'll look at in just a second. So you can't interpret these as probabilities, but you can interpret the signs as meaning less than or greater than. So for example, minus 2.47 means that males were less likely to survive than females, which is consistent with our calculation we did above. Passengers with a higher class, meaning 1, 2, 3, 3 being the highest, which in reality is the lowest class of ticket, were less likely to survive. And older passengers were less likely to survive because there's a negative coefficient there. And these are all significant. Now for class, I think, so here it's coded as numeric because there's 3 classes, but there's only 1 coefficient there. So really that should probably be a factor. So there's a couple ways to do that. One is you can put it in the model directly just by saying as.factor class. So that works. That makes a bit of a mess of the output. There's nothing wrong with this. This is perfectly fine. Another way to do it is just to redefine the class variable as a factor and then fit the exact same model. And now you get 2 lines for class. So why are there 2 instead of 3? Same as above. It has a baseline class, which in this case is class 1. And you interpret these numbers relative to the baseline. So class 2 was less likely to survive than class 1. And class 3 was even more less likely to survive than class 1. The others kind of remain unchanged. One kind of interesting thing, there's this residual deviance. So there's no, well, I guess you could define a residual for this type of model, but it is a bit different. The standard way of defining residual for logistic regression uses a concept called deviance, which we won't get into here, but it's a bit different. But the thing to know for now is lower is better. And so here the residual deviance is 1183. And for this model where we treated class as numeric, it's 1184. So they're very close. And the reason they're very close is because actually the effect of class is somewhat close to linear. It would be exactly linear if class 3 was double class 2, specifically if it was around 2.6. Here it's about 2.26, so it's almost double, but very close. So that's why the deviance for the factor model is actually very close to the one where we treated class as numeric. Okay. All right, that's all the models. That's the basic story. Next, I want to show you how to translate these things into probability using the predict function. So there's a function called predict. Predict is what's called a standard generic function, which means there's different methods written for different types of models. Here, M2 is a GLM model. And so there's a function called predict.glm that it's going to call here. And basically, you give it the model and you give it the data set, and it makes a prediction for what these probabilities should be. But it doesn't do the probabilities. It does these logit transform probabilities. So if we do this, here's our data set. I've added a column called preds M2. And these are obviously not probabilities because they're not between 0 and 1. So to do the transformation, you have to do this function. So this is the logit transformation, log p over 1 minus p. And this is the inverse transformation. It doesn't really have a name. I'm just calling it xbit. It's e to the x over 1 plus e to the x. So to get the probabilities, you have to do x bit of those things, which I need to define. And then if I pull out the data, so here I'm just printing the first 20 rows, and I'm printing the relevant columns, sex, class, age. These preds I just calculated and then converted to probs. So now these numbers are all between 0 and 1. And we could just take a look at the data. So the first passenger was a female, first class passenger, female, age 29. Probability of survival was 92%. So this person, let's see, did they survive? Let's add survived. She did survive. And the model says she was very likely to survive. The next one was a male in first class, a baby. And his chance of surviving was 72%, and he did survive. The next one was a female baby. She had a very high chance of surviving, higher than her. I don't remember if this was her mother or not, but if her mother had been 29, higher than her mother. and this child actually did not survive. And so on and so forth. You can go look at all of these. The first 20 are all from first class. So you can look at more. I guess we could do tail. All right, many of these are males in third class, and many of them died. Only a few survived. Actually, this one that survived is a female, and they have a low chance of surviving according to the model. Okay, one thing to remember above when we looked at the residuals from multiple linear regression model. It shortened the length of that vector because it took out some data. For the prediction, it doesn't shorten them. So this assignment works just fine, even though there were 51 missing observations. So there are 51 observations. M2 residuals is shorter than the size of the data. That's because the age variable was missing. But the length of this thing is fine. So you can predict M2 Titanic. I think it just puts in NAs. And so therefore this assignment works fine. Okay. Now that this has come up that there were 51 missing values, by the way, we could have seen that here on the summary because it prints 51 observations deleted due to missingness. Really, we should check to see if those 51 observations are drastically different in some way than the non-missing ones. So let's do this. I'm going to make a table of survived versus whether or not the age was missing. And, okay, so if the age, false means age is not missing. So most of this are false. Survival probability is 487 over 487 plus 771, 38%. When age is missing, it's 13 divided by 13 plus 38. It is a bit lower. So possibly we could investigate that further to see perhaps there's information in the data about what their age was. I'm guessing these are ones where the date of birth was missing or something like that. But maybe there's other information in the data that could help us guess their age, and we could put them back in. But we're not going to do that now. Next thing I want to do is try a model with interactions. Specifically, I'm curious if the chance of survival, I'm curious if the effect of sex on survival, whether you're male or female, depends on the class. We could also do age as well. That would be interesting. Maybe we can run that at the bottom. The reason sex and age might be interesting is maybe, older passengers help females get on the lifeboats, but basically they helped all the babies get on the lifeboats, whether or not they were male or female. So we could also consider an interaction with age as well. All right, but let's do this one. And here's the output. So in addition to the variables we had before, we have these things here. So let's talk a bit about how we interpret this, because this actually is a bit tricky. And let's start at the top. So the way you interpret the intercept, this is the log odds, this logit transform probability, when everything is at its lowest level. So female, class 1, age 0, you get this log odds. And if we do 4.762, all right, that had a very high chance of survival. the way you interpret this when there's an interaction in the model is this is effect of being male when you're in the lowest level of the one it interacts with, which is class. So this is the effect of being male if you're in first class. It's very negative. Let's compare that actually to the one above. So number is minus 3.9. The effect of being male when you don't have the interaction, so the additive effect of being male was minus 2.47. And the effect of being male for first class passengers when you have the interaction is minus 3.9. So it's bigger. The way you interpret the class variables, this is the difference between class 1 and class 2 for the lowest level of the sex variable, so for females. This is the effect of class 1 versus class 3 for females, not overall additive effect. It's for females. Age was additive, so we didn't interact age with anything else. So this is the additive linear effect of age. It's actually very similar to what it was above. The way you interpret these things, there's kind of two different ways of doing it. You could interpret it as one effect of being male for class 2 passengers, but you have to remember that this is a difference between this and this. So basically, for class 2 passengers, the effect of being male is minus 3.91 plus 0.04. So it's actually still negative. So for class 2 passengers, males were less likely to survive than females, according to this model. And the way you interpret this is the effect of being male for class 3 passengers, but again, you have to add it to this this effect. So it's larger, closer to 0, but it's still negative because minus 3.91 plus 2.27 is still a negative number. So for class 3 passengers, males were still less likely to survive than females. The other way is kind of just to flip the role. So you can interpret this as this is the effect of being class 2 for male versus class 1. So let's see. It's this plus this. So still for males, the effect of being in class 2 is still negative, even though this coefficient is positive because you have to add it to this. And for class 3 passengers, the effect of being male is also still negative because you have to add it to this. Okay. So, still worse to be male in terms of survival, and worse to be in class 2 and class 3. But this model has kind of adds nuance to what is the effect of these being male or female for the various classes and vice versa. Okay, that's a lot to take in. So what I like to do for this kind of model is to just make a data frame which has all the combinations and put in what the expected probabilities are. So I'm going to use the expand.grid function to create a data frame which has 3 columns, sex, class, and age. And it's going to have the 2 sex classes, and it's going to have the 3 classes, and 1 age. You have to put in an age. So I'm going to put in 30. Okay, so that's our data frame. And you can use the predict function to get the probabilities. And actually, it doesn't give the probabilities. It gives the logit transform probabilities. So you then have to pass those to xbit to get the probabilities. So if you do this, this gives us the probabilities. So female age 30 in class 1 is this probability. Male age 30 class 1 is that probability, still less than 50%. Female class 2 is lower than class 1 female, but still higher than male class 1. Male class 2 is 1.36. Female class 3 is now less than 50%. And male class 3 is 13%. Notably, you're had about the same chance of survival if you're a female in class 3 versus a male in class 1. Now we can compare these model-based probabilities to the actual survival proportions. So the way I'm going to do that is I'm going to take the data set group by class and sex and then summarize died, lived, proportion. And I'm also going to calculate the average age and print that out. Okay. Now these are pretty close, but there are some differences. So these proportions should match up to these. These are sample proportions. These are model proportions. And let's see, you see some differences. So 97.5 versus 96.5, 0.44 versus 0.344. So the sample proportion of survival for males in class 1 was 34%, but the model-based probability is 44%. Now, keep in mind what this actually means. This means up here, this model-based probability, we had to put in an age. So I put in age 30. However, the average age for males, age 30 was about the average age on the whole ship, but the average age of males in first class was 40.8. So that kind of explains why. And we know from the model that increasing the age decreases your survival probability. So that's, I think, why the sample proportion is 34%, because the average age in this group is 40, whereas this model proportion, which I had to put an age 30, is a bit higher. Any other big differences? 88, 88, 13, 14, 43 versus 49. It's higher here, 49 versus 43. And I think that's because this is the group with the lowest average age, females in class 3. Okay, so that's kind of, if you had just done this analysis, you might miss something because these sample proportions don't account for differences in the average age among these 6 different groups, whereas this model actually does account for that. So that's the benefit of fitting a model. Okay. All right, that's it for logistic regression.